Hello everyone, in this video, I will explain one of the topics in graph theory, specifically book embedding of graphs. Before we talk about book embedding, we first need to understand what a book means in graph theory. A book, also called a K-book, is a mathematical structure that consists of two main parts. First, the spine. The spine is a single straight line. Think of it as the binding of a physical book. All vertices of the graph that are placed along this straight line are called the spine vertices. Second, the pages. A book has K pages, where each page is a half plane. Imagine opening a real book. Each page extends from the spine outward into a different half plane. The edges of the graph are distributed across these pages. The key rule is, edges assigned to the same page must not cross each other. In other words, each page must contain a set of non-crossing edges. This is what we call an outer planar arrangement on each page. So, a K-book is simply a spine together with K half-plane pages attached to it. Now, what is book embedding? A book embedding of a graph G is an arrangement where all vertices of G are placed along the spine in a linear order, and every edge of G is assigned to exactly one page, such that no two edges on the same page cross each other. Two edges on the same page cross each other if and only if their endpoints alternate along the spine. For example, if we have edge A, C, and edge B, D, and the spine order is A, B, C, D, these two edges would cross. So they must be placed on different pages. The goal of book embedding is to find the most efficient way to embed a graph into a book using as few pages as possible. This brings us to one of the most important concepts, the page number of a graph, also called the book thickness. The page number of a graph G, written as PNG or BTG, is defined as the minimum number of pages needed to book embed graph G. In other words, we want to find the optimal vertex ordering along the spine and the optimal assignment of edges to pages so that we use the fewest pages possible while ensuring no two edges on the same page cross each other. The page number is a measure of graph complexity. A graph with page number 1 is called an outer planar graph. It can be embedded in a single half plane with all vertices on the boundary. A graph with page number 2 is a Hamiltonian graph, meaning it has a Hamiltonian cycle. For example, the complete graph K, which is the graph with 5 vertices where every pair of vertices is connected, has a page number of 3. This means K requires at least 3 pages for its book embedding. Book embedding is closely related to the concept of planar graphs and Kuratowski's theorem. A graph is planar if it can be drawn on a flat plane with no edge crossings. According to Kuratowski's theorem, a graph is planar if and only if it does not contain a subdivision of K, the complete graph on 5 vertices, or K. Why a complete bipartite graph on 3 plus 3 vertices as a subgraph? A subdivision of a graph means we are allowed to insert additional vertices in the middle of edges. For example, if we take an edge between 2 vertices and add a new vertex in between, that is a subdivision, now K. Y, as shown in this diagram, is a bipartite graph where one set has 3 red vertices and another set has 3 blue vertices, and every red vertex is connected to every blue vertex. This graph is non-planar and has a page number of 3. The connection to book embedding is a graph has page number 1 if and only if it is outer planar, and it has page number at most 2 if and only if it is a subgraph of a planar Hamiltonian graph. Book embedding has several important applications in mathematics and computer science. In VLSI circuit design, book embedding models how wires can be routed on multiple layers without crossing within the same layer. In sorting networks, book embedding relates to how efficiently we can sort using a stack-based model. Each page in the book corresponds to one stack in a multi-stack sorting machine. Book embedding of a graph G is the process of placing all vertices of G on a spine and assigning each edge to a page, such that no two edges on the same page cross each other. This concept is fundamental in graph theory and has important connections to planarity, sorting algorithms, and circuit layout design.